Welcome back. Today, we are jumping right into a genuinely fascinating explainer based on an engineering white paper dated August 25th, 2026. We're setting the stage for an absolute showdown between two entirely different ways of engineering, traditional digital control versus raw, analog physics. And we're going to look at this clash through the lens of a highly dynamic, high-impact, confrontational sport. We're talking humanoid robot tug of war. Now, I want to hook you right away with this powerful quote from our sources. Think about a tug of war match for a second. You might instinctively think it's just about who has the biggest motors, right? Or who can pull the hardest. But the engineers completely reframe this problem. The real crucible here isn't raw force. It's a matter of pure core stability and physical balance. It's literally about a machine knowing exactly where it stands, without needing a complex digital ruler constantly measuring its position. Okay, let's dive into this. Here is our roadmap for today. 1. The tug of war challenge. 2. Digital PID versus analog facts. 3. Visualizing core stability. 4. The energy efficiency clash. And 5. PUF, the silicon fingerprint. Section 1. The tug of war challenge, balance over brawn. So the white paper defines this robot tug of war as a high-dynamic, high-impact confrontational sport. And the strict engineering constraint here is beautifully simple on paper, but as you can imagine, incredibly hard to execute in the real world. The goal is to maintain the system's center of mass horizontally projected right inside the foot support area, all while an external pulling force is constantly trying to disrupt it. You're essentially battling to maintain physical balance against a constant, unpredictable injection of chaos. Section 2. Digital PID versus analog facts. Mapping physics to silicon. Now, what's really interesting about this slide is how engineers actually solve this. Look at how elegantly the fully analog computing system, or FACS, translates actual physical forces directly into hardware architecture. Instead of writing complex lines of code to simulate physics, the physical entities actually become the electronic components. Body mass and inertia map directly to node capacitance. Ground friction, that becomes the admittance matrix. The external pull of the rope is quite literally an external current source injecting into the system. And the center of mass offset is simply the node voltage. It's brilliant. It totally bypasses the need for a digital clock or code. The physics is the hardware. And because the physics is built right into the hardware, we get something incredible. The analog memory creates what the white paper calls a center of mass lag filter, with a time constant of 0.2 seconds. This is not software processing. It's a physical, inertial filter built directly into the chiplet. So if the robot's foot suddenly slips, this analog delay prevents that rapid physical shock from instantly tipping the whole robot over. It gives the machine a natural built-in core stability completely independent of a central processor. Moving on to Section 3, Visualizing Core Stability, the brutal showdown. To really visualize this core stability, engineers put both paradigms head-to-head in a brutal 20-second simulated match. We've got identical 20-kilogram robots handling the exact same rope physics, and this brilliantly illustrates the difference. If you look closely at the microview chart on the bottom left, showing the center of mass over time, look at the solid blue line. That is the FACS analog system. It's a calm, smooth, continuous curve. Now look at the red line superimposed right over it. That's the digital PID system. It is an absolute mess of chaotic, spiky, high-frequency noise. To put this into perspective, think of the digital PID robot as constantly overthinking and just straight up panicking. It's sweating, jittering, and calculating its position every 5 milliseconds in rigid, stepped logic. This creates massive high-frequency microtremors of about 0.035 meters. It's literally vibrating on the floor, causing the motors to whine in distress. But in stark contrast, the FACS robot is completely zen. It operates with a continuous analog force. It's just feeling the pull and reacting instinctively like a biological muscle, with incredibly smooth center of mass jitter under 0.01 meters. Section 4. The energy efficiency clash, dissipation and heat. Now, on the outside, after 20 seconds, the match was technically a dead tie, but internally, the toll was vastly different. Look at this isolated energy data graph showing the center of gravity velocity fluctuation distribution. The blue bars represent the FACS system. Notice how highly concentrated they are? It's handling the energy smoothly and saving immense amounts of power. But look closely for that tiny red bar representing the digital PID system, way out there on the negative axis. Its energy is entirely scattered. It's basically fighting itself with every single micro adjustment it attempts to make. So the crucial point is this number right here, 30x, because the digital PID system is constantly stepping, jittering, and dealing with high-frequency switching just to simulate balance. It actually wastes 30 times more power than the analog system. And as you know, wasted energy doesn't just magically vanish, it turns into heat. This leads to a simulated temperature rise 3 times higher than the fax system, bringing massive overheating risks during a sustained sports match. And finally, Section 5, PSUF, the silicon fingerprint. Let's step out of the raw physics for a second and get to the white paper's visionary confetti reveal. PUF stands for Physically Unclonable Function. See, in the manufacturing of these analog chips, there are always tiny microscopic random variations. The engineers didn't try to fix this or engineer it out. No, they completely harnessed it. The inherent offset voltage of each chip becomes a unique, unforgeable hardware signature. It's a literal silicon fingerprint. Let's move to and see how this builds into an insane competitive advantage. Upon power-up, the chip instantly translates its random mismatch into a precise centerline compensation voltage. No calibration required. No external cameras needed to orient the robot. Zero remote control. Within 1 single microsecond, the robot autonomously locks into its perfect starting stance with an error margin of less than 1 millimeter. It effectively gives the machine an autonomous physical instant. But let's push this imagination further, especially for the future of robot sports. If this PUF silicon fingerprint allows a robot to instantly know its own stance and signature, it can absolutely be used in multiplayer matches. Imagine an entire team of robots instantly using their hardware signatures to identify their specific teammates, recognize their opponents, and map out distinct relative spatial positions on the field. And they do all of this instantaneously, without relying on laggy visual processing or a central remote server. It's a whole new ballgame. Which leaves us with this final provocative thought. In these future matches, technology defines the stance, but humans still define the moment. The referee blowing the whistle is still human. But with machines holding perfect, autonomous physical instincts baked right into their silicon, seamlessly identifying each other and reacting like real athletes, how far will the realism of future robot sports evolve? When the whistle blows and pure, unadulterated physics takes over, we might just be sitting back to witness a whole new era of spectacular, hyper-realistic athletic entertainment. Thanks for joining me on this explainer, and keep wondering about the limits of tomorrow's technology.